Good day once again, students. Today we are going to talk about the electron wave. Electron waves. I know some of you will be wondering, what does this teacher mean by electron wave? No, it's not crazy. You see, in our last class, we discussed about the nature of light. We agreed that light has dual nature. Light behaves both as a wave and as a particle. We already agreed that light behaves as a wave because it undergoes diffraction and interference. Because we know right from time that anything which undergoes diffraction and interference is a wave. We also proved that light is made up of particles. And we prove this with the photoelectric effect. If light, which is energy, could be a wave, or could be a particle, what about matter? I told you earlier that if you have two baskets and you decide to put anything at all in the universe, separate them into these two baskets, one basket, all energies will go in there, and the other basket, matters will go in there. We took light, which we traditionally know as energy, and we will have definitely dumped it into the energy basket. Now we are confused. Do we dump it into the energy basket, or we dump it into the particle or matter basket? Now light can answer both call. It can answer the call of the energy basket and the call of the particle basket. If this is possible with energy, which is light, what about matter? Can matter also be wave? Can matter also be wave? So that's why some authors will write in their textbook the matter waves. The matter waves. I call it the electron wave, because electron is a particle of matter. Now, if this is the case, can electron exhibit wave property? If electron can exhibit wave property, that means proton can exhibit wave property. That means neutron can exhibit wave property. That means atom can exhibit wave property. That means elements can exhibit wave property. That means compounds can exhibit wave properties. That means molecules can exhibit wave properties. That means macromolecules can exhibit wave properties. That means organisms can exhibit wave property. That means you and I can exhibit wave property. Is that actually true? Is that actually true? This is what we are looking at today. In the year 1924, a Belgian scientist, Louis de Broglie, but most of us call it de Broglie because of the spelling. Many of us call him de Broglie, but it is actually pronounced de Broglie. De Broglie. Hypothesize that if light can behave as particle, he suggested, he hypothesized that electron, which is a matter, could also behave as wave. And that if electron can behave as wave, it must have, of course, a moving electron can behave as wave. If a moving electron can behave as wave, that means it must have a wavelength. And it suggested that that wavelength, lambda, of the electron equals to, of course, Planck's constant divided by the momentum of that moving electron. Of course, you know momentum is mv. That means lambda of that electron will be equal to h divided by mv. That means the higher the faster the electron, the smaller the wavelength of that electron, and the smaller the wavelength of the electron, that means from energy equals to hc over lambda, that means the smaller the wavelength of that electron, that means the larger the energy possessed by that electron, now behaving like a wave, a particle wave. That was his proposition. That was just a hypothesis at that time. Later, two other scientists, Davidson and Mr. German, Edmund German, and Clinton Davidson and Edmund German, I tend to forget the other name, they worked. Not only them, when the hypothesis came up from Mr. de Broglie, many scientists started researching. They went into research. They started researching and researching and researching until the first duo, these two guys, Mr. Clinton Davidson and Edmund German, they were able to experimentally confirm the hypothesis of Mr. de Broglie. They found out that electron could actually undergo diffraction and interference. Diffraction and interference. So we are here today to show you this diffraction. So many of your books also call it, this topic, electron diffraction. So far so good. Write what I have just given to you. Write this down. First, the topic, Louis de Broglie or de Broglie hypothesis. In the year 1924, Louis de Broglie hypothesized that if light could behave like both a wave and particles, both like a wave and particle, it is highly likely that matters such as electrons could also exhibit wave properties. Write this down. Let us continue. He proposed that if electrons could travel in space like a wave, the wavelength lambda of electron could be represented by the equation this: lambda equals to h over p, where h is the Planck's constant. We should know the value and it will always be given to you in your exam, and p is the momentum of the moving electron. So from there we remember that p equals to mv, where m is the mass and v is the speed of the electron. So we have the final equation to be like this. Write this also. Write this page and write this page. Now, the de Broglie or de Broglie hypothesis led many scientists to go into research of the wave nature of matter, until two scientists, Mr. Clinton Davidson and Edmund German, later confirmed experimentally the diffraction of electrons by single crystal of nickel. Because if we are diffracting electron and we are saying electron has wavelength, electron must pass through a gap. Electron must pass through a gap to show that the diffraction of electron, the gap the electron will pass through must be small enough, must be equal to the wavelength of that electron. To be equal to the wavelength of that electron. So they were looking at a particular wavelength of the electron. That wavelength of that electron, of course, which could be varied, because when we say the wavelength of the electron could be varied, if I move the electron faster, the wavelength will decrease. If I move the electron slowly, if I move the electron faster, of course, high velocity, the wavelength will decrease. Low velocity, the wavelength will increase. So we can vary the wavelength. How do we vary that? You will see soon. So by varying the wavelength, they got to a particular wavelength which coincided with the gap between the atoms of particle in the crystal of nickel. Between the atoms of nickel. Of course, nickel is a metal. Atoms are arranged in lattice. Of course, metallic lattice. So they found out that at a particular wavelength of electron, diffraction pattern shows. That means the wavelength of that electron coincided or became very close to the gap between the atom or the atomic arrangement of what? Of nickel. So we saw diffraction. You saw diffraction. So wow. So for this to happen, that means for us to see diffraction pattern on the screen, that means that electron is behaving like a wave. So this diffraction confirms the wave-like property of electrons. After this first attempt, electron diffraction experiment has been performed and still being performed in thousands of laboratories around the world to prove the wave property of matter. Let's now look at electron diffraction. Electron diffraction now. This is the setup of electron diffraction. Electron diffraction. This is the cathode, which is a heater, and this is the anode, a cylindrical anode with the hole. This one is not new to you, at the center. And of course, here the speed of the electron can be adjusted here by varying the what? By varying the voltage. By varying the voltage. By varying the voltage. The speed of the electron can be adjusted by varying the voltage there. So, vary the voltage, this became so hot, an electron goes off. Electrons go off from it and travel, and of course when it gets to it attracted to the anode. Electron attracted to the anode, that is the anode there. Electron attracted to the anode. And what did we see first? What did we see first? Without anything there, and of course we have a tube. This tube is all evacuated tube. The tube is a vacuum because we don't want the electrons coming to collide with any other thing. So, and the end of this glass tube is a glass. The end, the bottom part of it here is coated inside with what we call phosphor. It's a phosphor screen. Phosphor, the phosphor will flash. You give flash. You are used to this. You know this before. We give flash when it is heated by high energy electron. When high electron strikes it, it gives a flash. So the electron coming from here, came out here and moved straight into. And at the end, gives a flash. It gives the flashes there. You have flashes here where it hits the phosphor screen. You see the flashes, tingling flashes. That means, because we will not see this light, this electron as light, it will not be visible. The only thing we will see visible is the tingling here, the flash here. That means electron has traveled from here through this anode into that place to hit it. For those of you who have a syllabus where we have done fermionic emission, you understand what I'm trying to say here. Now, this has happened. Now that this has happened, scientists now decide to place a matter. What we do today is we place there, we place graphite. The atomic layer of graphite is small enough. The gap between the atomic layers of graphite is small enough to cause the diffraction of this electron. What did we notice? We now notice that instead of just that one at the middle, we still have that at the center there. Then we now have circular rings at the end of our tube. We have circular rings like that. At the end of our tube, we have circular ring like this. We have circular rings. This became a surprise. Without this, we saw the electrons just here alone, because we saw the flashes just here alone. Without the matter there, without the graphite there. This is graphite. This is graphite. But now with the graphite, the flashes appears here in a ring, another ring, another ring. That means ring, circular ring, darkness, circular ring, darkness, alternating circular ring and darkness. When we turn this tube to you at home or in your class, what you see on the computer is, now I turn this tube to you like a bulb. This is what you will see. I'm going to tell my cameraman to switch off the light. Now, please, can you switch off the light for me so you can see it very well? This is exactly what we see when it was turned to us. Don't mind the darkness, just listen to me and understand my explanation. So we saw alternating brightness, darkness, ring of brightness, and darkness. An alternating ring of brightness and darkness. What does this remind us of? It reminds us of what? Interference, which causes the diffraction. Remember, diffraction of light. It reminds us of this. That means the area of light is area of constructive interference, the bright area where the electrons interfere constructively. Remember the single slit experiment. And area of brightness where the electrons interfere constructively, and the area of darkness where the electrons interfere destructively. This is a wave. This is a wave property, interference and diffraction. So to bring it out properly for you, we draw this other Newton diagram for you. So this is what we have seen. This is what we have seen. Just like what you have in your fringe pattern. So we have circular rings of electron flashes in the green, and darkness. So we have alternating. So this is diffraction, a diffraction pattern. We also notice that if we try to increase the speed of the electrons by changing the voltage, what do we see? Because we said lambda equals to h over mv. If we increase the speed, lambda will become smaller. We find out that the pattern becomes shrink because wavelength reduces. Don't forget that. How it spreads out. Because for this, n lambda equals to 2d sine theta. So once lambda decreases, sine theta will also decrease. So the pattern shrinks. Again, when we increase the speed of the electron, what happens? The pattern shrinks because lambda has reduced from here. We increase this, wavelength reduces. If wavelength reduces, therefore sine theta also reduces. The pattern shrinks together. But this is the pattern we see at the on the phosphor strain at the end of the tube. At the end of the tube there. At the end of the tube there. That is what we have seen, the circular arrangement. For this to have happened, scientists now said, for us to have seen this, it actually applies that when the electron passes through the graphite here, then it spread out. The electrons spread out. Some of them now meet at some point and interfere constructively to form this ring of brightness, and some meet destructively to form this ring of darkness. So that's why we have alternating ring of bright and dark, just like our fringe in the light pattern. So that means passing through these, the electrons, this is electrons, electrons coming from the cathode ray, passing through the graphite. The gap between the atomic layers of graphite is enough to cause them to diffract, because that gap equal to, at a particular wavelength, equal to the wavelength of the what? Of the electrons coming from our adjustment, because we can adjust the wavelength by adjusting the voltage, by adjusting the velocity. We know this, and we see diffraction, and we call this wavelength where the diffraction occur the Broglie or the Broglie wavelength. That wavelength is called the Broglie or the Broglie wavelength. And it is different depending on what matter you place there. So this is what we have seen. Now, if we place something like the nickel that was used initially, and we zoom in to view very well, you can see the electrons, flashes of the electron. And because you can see the flashes of electron, it can actually show us the arrangement of the atom in a particular crystal. This is crystal of what? We are talking about crystal of nickel. So it can actually show us the arrangement of of atom in a particular crystal. So we also use this process of electron diffraction to probe into matter so that we know the arrangement of the atom, because the atomic gap, the gap between the atoms, will serve as what? As the diffraction gap, the gap where diffraction will pass through. Once we adjust the wavelength and it gets to that, can I have the light on, please? Once we adjust the light and it gets to that wavelength, it gets to that gap, then we see clearly our diffraction. So we can use this to probe matter and see the arrangement of atom in matter. And that's what we also call electron diffraction, to probe matter, to probe for probing of matter. That is the arrangement of atom in the matter. You can see that. Now that we have seen this, we are humans. Our car, and we are matters. Our car is a matter. The house we live in is a matter, although it cannot move. Our dog is a matter. It can move. We can move. Does it mean we can undergo diffraction? That is the next question I want to ask. Now that wave nature of matter has been confirmed, can you consider yourself a wave under any condition? If electrons can move, and the speed of electron can be adjusted, and at a particular time it will have a wavelength which will cause diffraction through a particular gap, can your own speed at any time cause diffraction through a gap when you pass through a gap? Let's reason that and see. With this arrangement, assuming you are about 65 kilogram man or boy, you are moving through a gap of about 0.8 meters, not up to 1 meter, maybe your door is about 0.8 meter, and you are speeding through that door with another reasonable speed of 3 meters per second. What will be your wavelength? Let's calculate your wavelength. Again, your mass is 65 kilograms. And your velocity is 3 meters per second. And you are also moving through a gap of 0.8 meters. If we use the de Broglie equation to find the your de Broglie or the de Broglie wavelength, what are we going to get? Mass of the man is 65 kilograms. The speed of the man is 3 meters per second, and the opening is about 0.8 meters wide. If we are getting your de Broglie wavelength, your de Broglie or your de Broglie wavelength is h over mv. This is h, Planck's constant, divided by your mass is 65 multiplied by 3. This is what we are going to get as your wavelength. This wavelength is so small, is so tiny compared to this gap. Compared to this gap, and we all know the rule. For us to see appreciable diffraction, the gap must be similar in size or equal in size to the wavelength of the moving wave. So you are the wave now. We consider you as the wave moving past the gap. This gap is so much wider than your what? Than your wavelength we have calculated. So it therefore means that we will not be able to see any diffraction pattern if you do that. Can we do anything so that you can see a diffraction pattern? Think of it. What can we do so that you can see a diffraction pattern? That means we either need to decrease this gap so much to fit this wavelength, or we increase this wavelength so much to fit the gap. Let's do one of these now. And if we are going to decrease this wavelength so much, or increase this wavelength so much to fit into this gap, that means we have to. Your mass cannot be increased. What can be increased here can be your speed. We increase the speed so much so that the answer here will also be 0.8. That will be too much of a speed which cannot be achieved by you and I. Because this is very high, the answer here will be, oh, we need to decrease this speed so much so that this becomes high enough to be this. That cannot be achieved. That cannot be achieved. This is a reasonable speed for a man. Now, what else can we do? Can we decrease the gap of the door, of the gap so much to fit into this? If we do that, you will not even be able to pass through. Of course, if you cannot pass through a gap in the first place, there will be no diffraction. So you can see that for now, scientists have no way to show diffraction pattern with human or large particles. So we consider ourselves as large particles. Maybe tomorrow, because many of the scientific discovery today, they were like dreams years back, hundreds and thousands of years back. They were like dreams. Nobody could even think of it or just imagine it. It looks crazy. Maybe tomorrow, scientists will be able to make human waves that you and I will be able to travel in space without going through the helicopter or the airplane. Maybe tomorrow it will be possible. Maybe tomorrow human diffraction may be possible, or diffraction, maybe human will be able to move like wave tomorrow. That is yet unanswered, and we cannot say no to any scientific reasoning because discovery happens every day. So students, you have been able to see this now, that matters behave both as particle and as wave. So in that basket also, just as you are confused that you bring your electromagnetic wave, you don't know where to drop it. Do you drop it into the energy basket or the wave basket? You don't know. Now you also bring your matter now. It has caused confusion now. Do I drop matter into energy basket or into wave basket, you are confused now, because matter also has dual nature, just as light has dual nature. So you know the duality nature of light and the duality nature of matter. For the duality nature of light, you remember the equation energy equals to what? HF, which is hc over lambda, and that means energy behaving like matter. And you also know now that matter behaving like wave, lambda equals to h over mv. Don't forget this. Light behaves as matter or particle, particle behave as wave. So students, this is where I'm going to stop. This is where I'm going to stop. This is where I'm going to ask my camera to be stopped. And this is the end of our topic, the nature of particles or electron wave. And I believe you have seen and you understand fully the topic. Don't forget, this is for electron diffraction. This is electron diffraction experiment, and anything could be put there. When there is nothing there, you don't see that. When there's something there, of course, you know, it scatters like that. There is diffraction, which I have shown you. So students, should you have any question, do not hesitate to contact your teacher, and I will be very happy to send back another. Just write your email and I will send back another video to you within 24 hours to answer your question, to clear your doubt in 24 hours. Once again, this is Teacher Afiz saying good day and God bless.